Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is phase equilibrium, and the section in the textbook is 16.6. Here are the learning outcomes. At the end of this, you will know how phase equilibrium can be determined using the Gibbs function. You'll understand how distillation works for purification of a mixture component. You'll be able to use Raoult's law to determine the equilibrium composition of a binary two-phase system, and you'll be familiar with Henry's law for dilute solutions. So first I want to talk about phase equilibrium of a single component. And so here I have, for example, liquid water boiling and it's forming water vapor. And I can think of the boiling process as a chemical equation where I have water in the liquid phase, I'm adding heat to it, and I'm becoming water in the vapor phase, in the gas phase or vapor phase. And this is more or less a chemical equation. And so we know that at equilibrium that our Gibbs energies are going to be the same, and we can actually see that. So for example, let's just take a mixture of liquid and vapor. Again, one component, two phases. And let's just talk about the total Gibbs energy of that system. So the total Gibbs energy, or Gibbs function G, is going to be equal to that of the liquid and that of the vapor. So it'll be the mass of the liquid, I'll use a subscript F for liquid, lucid, and then times its intensive value of G, so G sub F, and then I'm going to have that of the gas phase, M of the gas phase, and G of the gas phase. Now remember, G is equal to H minus TS. So although both of these are water, both of these G's, they're markedly different. Clearly they have markedly different enthalpies and entropies if they're in their liquid or vapor phase. So these little values of G are very different even though they're in equilibrium. So now we can go ahead and take the differential of this. So let's talk about dG, and we'll do that at a constant temperature and pressure. So I'm going to do the differential of that. Little g, that's an intensive property, so that's going to remain the same. So I end up with dm of f times gf plus dm of g sub g. So that's just the differential amount of liquid and differential amount of vapor. And one of the things is that clearly if I'm boiling, whatever liquid boils away becomes vapor. And so I know that dm of f, the amount of liquid that I lose, is just equal to minus that I get in the vapor phase or in the gas phase. So those are just the same magnitude of opposite sign. So over here I could go ahead and just put dm of g in for that term right there. So this all becomes g of f minus g of g times dm of g. There's a minus sign in there. That's what dg is at constant temperature and pressure, and we know, we've looked at this before, that has to equal 0. So I could go ahead and divide by my differential mass, and that just simply tells me that gf is equal to gg, or the Gibbs energies are the same. So go ahead and come back to this equation, g is h minus ts. H and S are markedly different of the two, but when I combine them in this way, if they're in phase equilibrium, their values are going to be the same. So let's just go ahead and verify this to make sure we're happy with it. So here I'm looking at the saturation table for water. So this is pure water. And let's just go ahead and take our values at, we'll go down here at the bottom at 95 degrees. And let's go ahead and just calculate what the two values of G are. So first I'll do it for the liquid phase. So G is going to be H minus Ts. And so now I'm going to use the liquid phase values for that. So pulling those off the table, I have 398.09 minus the temperature. 95 degrees Celsius is 368 Kelvin. We use absolute temperature on that. And then my entropy value is 1.2504. And if I do that arithmetic, this comes out to about minus 62. And those are, the units are going to be kilojoules per kilogram. And now I can go ahead and calculate what G of the vapor phase is, or G sub G. And so that's going to be 2667.6, much larger if it's in the gas phase. Temperature is still 368. I'm comparing them at the same temperature. And its entropy is much larger as well. It's in the vapor phase, 7.4151. And if I do that arithmetic, it comes out to about 62 kilojoules per kilogram. So all I did was went ahead and verified that yes, GF is equal to GG when I have two components, two components in the two different phases. All right, So let's talk a little bit about vapor pressure now. So now I'm going to go ahead and look at mixtures of things. So for example, let's go ahead and take I'll just take pure water, okay, but now I've got an open container, and so maybe it's at some temperature well below boiling. Let's just use the atmospheric pressure and say 25 degrees C, and we've looked at this before. We're going to have some water vapor in the air. So this is otherwise air. We kind of looked at this in chapter 14 as well. So we've got an air-water mixture. And so if I want to talk about what the value of the Gibbs function is of the water that's in the vapor phase, so that value of G, well, that's going to be equal to G star, and then I've got a mixture of water vapor and gas vapor, so I need to go ahead and account for the fact that it's a partial pressure. And so we saw this term before, where we have RT and the natural log of its partial pressure expressed in atmospheres, and that right there for ideal gas mixtures is just the mole fraction Y sub I. And so then if I look at the Gibbs function of the liquid phase, so here I was looking at it, I'll call it G sub G, that of the water mixed in air, and then I've got this of liquid. If this is pure liquid water, and air doesn't really dissolve in water, so this is pretty much pure water, I'm going to have G in the liquid phase. And so G of F, we'll call it GG up there. So G of F is just going to be HF minus T SF, and I can go ahead and get that for the water phase. So if I go ahead and calculate that, and I can go ahead and find out the absolute value of the Gibbs function of pure liquid water, that's about minus 3.07 times 10 to the 5th units on there, kilojoules per kilomole. And then all I'm going to do is go ahead and calculate my value of G in the gas phase, and it's going to be a function of the vapor pressure. It's going to be a function of how much water vapor I put in there. And if I go ahead and calculate that, and this is a plot of that function, I actually calculated it using a software package called Cantera, which is similar to EES, but it uses the same reference point for all components, so it makes this analysis or this demonstration a little bit better. So here I've got my value of G, that's that value of G right there, and I'm plotting it as a function of its partial pressure expressed in atmospheres. And so if I look, and I'm looking for a value at about 3.07 e to the minus 5, that's right about there. And so if I look at that and drop it down, I realize I'm just a little over 3%. And so if you were to go and look at that's what the saturation pressure is at 300 Kelvin, or about 298, about room temperature, which is exactly what you would pull off the table. So what we see is, I've said before that there's always some water vapor in air. If you want to know how much, well, the vapor is doing is it's always setting its Gibbs energy. It's putting enough water in there such that its Gibbs energy is equal to that of the liquid phase. If I raise the temperature, this Gibbs function is going to go up, this Gibbs function has to go up, and so therefore that partial pressure term has to go up, and that continues to happen as you vary the temperature. All right, I want to talk a little bit about mixture equilibrium. And so now what I'm going to do is start looking at two components. We're now actually, I've got two components in both the vapor phase and the liquid phase. And so we can go ahead and look at this diagram here. We'll have red and blue. And notice I've got blue, you could think of that as the liquid. The red up at the top is kind of the vapor. But really, the vapor phase is the top. The liquid phase is the bottom, and I have two components in each of those. And so two things that are very similar, like ammonia and water is a common mixture, or water and ethanol is another very common mixture. And so what I know is if I was to look at G in the vapor phase of the blue, that's going to equal to G in the gas or in the liquid phase of the blue. And then the red is also going to be true. So G in the gas phase of the red can equal to G in the liquid phase of the red. Now those two are not necessarily equal. The red and the blue can be marked with different values, but their Gibbs energy in the vapor phase and the liquid phase are always the same. And so that's kind of interesting, because if I go ahead and change the composition, maybe I go ahead and put more red molecules down over here, it's going to go ahead and change the composition of red and blue in the top, because it's got to be maintaining both of their Gibbs energies to be equal to the same. And so if I was to go ahead and plot, and so I could go ahead and plot what those equilibriums are. So at a particular temperature, this right over here might be the liquid phase composition, and that right over there would be the vapor phase composition when their Gibbs energies are the same. And on the bottom here, I'm kind of showing diagrams Over on the far right would be like pure blue. Over on the far left would be pure red. And so here at a particular temperature, at chemical equilibrium, chemical phase equilibrium, there's the composition of the vapor phase, there's the composition of the liquid phase. Those Gibbs energies are the same, but what you realize is that the liquid is much richer than the vapor phase in blue. It's got much more blue and much less red, or vice versa. The vapor phase has much more red than blue, kind of as I show in the diagram here. And this gives the idea of distillation, because what I could do is now just capture that vapor phase and then go ahead and condense it down. And if I was to do that, now this, what was in the vapor phase is now going to become the liquid. And then if I was to go ahead and boil that again, what ends up happening is it's going to become again yet more pure in red. And so what effectively I've done is I took my vapor, condensed it to a liquid, and then when I went ahead and boiled it again, and now I realize I've got something that's very, very rich in red. And I can continue that process, and that's what is distillation. And that's why you can end up purifying components. For example, I'm purifying red out of a solution of blue, right? And so you can imagine if I had beer, it would be a weak solution of ethanol. I could go ahead and do that and end up with a very, very strong, like a liquor that's very strong in ethanol through a distillation process. So it kind of brings up this idea of the Gibbs phase rule, and I want to review the Gibbs phase rule. We looked at it before, so let's first just do some kind of thought problems here. So first I'm going to just take pure water on the left here, and this is compressed liquid, so I'm below the boiling point. I'm in a piston cylinder device. This is just pure water, and so maybe it's at atmospheric pressure and 25 degrees C. I could go ahead and turn it to 30 degrees C, so I could go ahead and raise the temperature and the pressure, but I could independently go ahead and maybe put some weights on here, and I could independently change the temperature or the pressure. And so both the temperature and the pressure are independent, right? Two intensive variables, and we know from the state postulate that T and P are independent as long as I have only one phase. Now, if I was to go ahead and raise the temperature enough that it began to boil, again, I've got pure water here, just one component, but now I've got this boiling. What I know is that now T is a function of pressure, and in fact, it's going to be equal to T sat at that particular pressure. And if I change the total pressure, put a weight on there, this temperature is going to change as well. And so what I've done is that no longer are T and P independent once I have two phases. So I have two phases there. I only had one phase over here. So what I realize is as I increase the number of phases, I decrease the number of independent variables I have. Suddenly T and P were not independent. Let's go ahead and expand this now to things that are more than one component. So now imagine I've got this mixture of red and blue, right? And so I could go ahead and change the temperature. I could make the temperature go up and down. Again, I could go ahead and put some weights on it. I could make the pressure go up and down. But also, I could go ahead and just add some more red to it. And what I would find out is I can go ahead and change the mole fractions. And so I can go ahead and make the mole fraction of red go up and down independently. So I'm able to change kind of dial on three different things. But now let's go ahead and raise the temperature enough that this solution begins to boil. And if it begins to boil, what happens now is that its boiling point and the composition up here is going to be fixed depending on what my temperature was. Remember, here's my diagram. At a particular temperature here, the composition of the liquids and the vapor are fixed because their Gibbs energy needs to be the same. And if I was to go ahead and change the pressure, maybe I'm going to drop it down to a lower temperature, I would be changing the compositions in the liquid and the vapor phase. So what that tells me is that I could go ahead and T now becomes a function of the mole fraction that I have. So I've sort of lost this independent variable. These two became tied. Now you might wonder what happened with pressure. Well, pressure is still independent. If I were to go ahead and add pressure over here, it's going to move this diagram a little bit. These two will remain tied to each other, but it would have a new value, all a function of that pressure. And one way to think of it is this is actually kind of a three-dimensional diagram. If this was my pressure axis here, imagine this football that's kind of expanding out. And so there'd be this diagram or more or less a three-dimensional surface over here. And so at each particular pressure, I could take a slice and get it. So normally you see these diagrams, these binary phase diagrams, at a particular pressure, like atmospheric pressure, for example. Well, that brings up the Gibbs phase rule. And here's the way the book writes it. IV is the number of independent variables. So for example, back to my pure water, I had two independent variables when I had one phase. The number of independent variables is equal to the number of components minus the number of phases plus 2, right? So independent variables, number of components, pure water, I had 1. Well, if I had 1 phase, I had 2 independent variables. If I had 2 phases, I only had 1 independent variable, and we saw that here. Now, as I increase the components, so maybe I put it up to 2 like I did on the bottom, what you realize is now you've increased the number of independent variables you have. You now have t, p, and y. But if I go ahead and change the number of phases, go to 2 phases, I drop that down, and I drop myself down to 2. So there's the idea of the Gibbs phase rule. This keeps going on. If you have 3, 4, 5 component mixtures, you begin to have more and more independent variables. And they start becoming all the different mole fractions that you can have of one component in another. I want to briefly just mention azeotropes because they're sort of interesting. The textbook doesn't necessarily talk about azeotropes. But I just showed a binary phase diagram below that's an ideal one. Some of them look like I showed here, where there's this thing where they begin to tie, and effectively these lines cross. And this is called an azeotrope. And in fact, the water ethanol system has an azeotrope. Has an azeotrope. It looks something like this. And what that means, so over here would be pure ethanol on the left, and this would be pure water. And what happens is, you can imagine, let's go through that distillation process. As I step down here, I'm going to get myself sort of caught there, and I'll never be able to get any purer than that point. That's where the azeotrope is. And in the water ethanol system, I think it's about 95 or 96% ethanol. And you can't distill anything any stronger than that. It's obviously pretty strong ethanol, but it comes out that you can't get 100% pure. Not all materials that have azeotropes, some mixtures do, and it's really just a function of the chemistry of the particular components that you put together. All right, now I want to go ahead and talk about Raoult's law. And so Raoult's law applies against a two-phase system. So we'll start off with one phase and we'll expand our thought problem down to 2. So first, we'll just have pure water. I'm showing over here. So we'll go back to pure water. But I've got pure water, and then I've got some water vapor in air up on the top there. Right? So this is my water vapor in air above pure water, like above a lake, for example. And we were able to approximate what that partial pressure was. We were able to say, oh, we knew that the partial pressure is equal to P sat. And so we could find the saturation pressure of water, and we could determine what the partial pressure was at a particular temperature. Okay? So now my question is, what if I now had a 2-component mixture? So maybe I had a bunch of red in here in the liquid phase in the blue, and I want to know how much red I'm going to have up in the vapor phase above it. So I've got blue and red, and then blue and red up on the top. And what I would expect is that, well, I'm kind of looking at this, the partial pressure in the vapor phase is probably a function of how much that I have in the liquid phase. And so that comes the idea that I'm going to say that the partial pressure is going to be equal to, which is y sub I times p, that's just the mole fraction of the total pressure, must be a function of how much I have in the liquid phase. So I'll call that x sub I times p sat. And so if I had pure water, xi was equal to 1. That's pure water. So I'm using x as the mole fraction in the liquid phase, y is the mole fraction in the vapor phase. And so what I've done is I've just kind of generalized this, and I'm weighting it by the amount that I have in the liquid phase. As I add more and more red, I would expect that the vapor pressure in this is going to increase. And once I have all red down here, I'm just reducing to this idea of Pi equal to the saturation pressure at that particular temperature. All right. So what I could do now is just go ahead and get another expression for this, and I find out that P of the saturation is going to be equal to Yi over Xi, so I'm just dividing over here by the total pressure. So if I go ahead and divide through by Xi, I'll find out what my saturation pressure is. And so that's the idea of Raoult's law. So I have 2 components, right? This is my liquid phase composition. This over here is my vapor phase composition. And P saturation of, say, component 1, well, it's going to be equal to Y1 over X1 times the total pressure. But I also know the saturation pressure of 2 is going to be Y2 over X2, right? And so I've got component 1. This might be component 1. This would be pure component 2. And these are my mixtures. And I also know that the mole fractions have to equal 1. So Y1 plus Y2 have to equal 1. X1 plus X2 has to equal 1 as well if I have a binary mixture. So from here, given some saturation pressure information from the 2 components that I have, I can go ahead and determine what the relative fractions are in the liquid phase and in the vapor phase. One last thing I want to mention is Henry's law. And Henry's law relates to dilute solutions. So what I'm going to do now is take Raoult's law and just look at it when I have a really, really dilute solution. And so what I'm looking at here is maybe I'm saying I've got all this red in the vapor phase, and it's only weakly soluble in the blue. There's not a whole lot in there. And so I would assume that the mole fraction in the gas phase is going to be proportional to the amount I have in the liquid. And if I add more into the vapor phase, I'm going to go ahead and drive a little bit more into the liquid phase. So there's some sort of proportionality constant that I have in there. I can multiply this equation just by the total pressure. So I'll just multiply the left-hand side by the total pressure. Yi in the gas phase times P is the partial pressure of that in the gas phase. And now I've got the total pressure times the mole fraction in the liquid phase. And so that tells me I can find out what the mole fraction is in the liquid phase. And so these are proportional, so it's going to be equal to the partial pressure over some constant. And I'm just going to call that constant H, which is Henry's law. So this right over here is Henry's law. And you can get values for Henry's law constant here. The book has them in 16.2 for various components as a function of temperature. And here's the number that you put into H. And so you can go and determine what your composition is in the liquid phase, given the partial pressure, or vice versa. What's the partial pressure in the vapor phase if you know how much you have in the liquid phase? And remember, this only relates to dilute solutions. This is sort of a linearization of Raoult's law.